So, we quickly recap what we have done so far for small oscillation and then we will continue. So, we started off by writing the kinetic energy, potential energy V as B I j q I q j and T as A I j q I dot q j dot, right. So, we did that and then we have so Aij's and Bij's, they are found to be real symmetric matrices, and from there we wrote the Lagrangian, then the differential equation. So, the Lagrangian and the differential equation was, if I am not very wrong, so we took a trial solution essentially for the differential equation, which was A I j q j double dot plus B I j q j equal to 0, and we took a trial solution of the form q j equal to A j e to the power I p t, because we are assuming oscillatory motion. So, we took this trial solution. When we substituted in here, we got an equation of the form, we got an equation of the form minus p square A I j A j plus B I j A j equal to 0, and this is a set of simultaneous linear equations. So, if and only if the determinant of this coefficient term is equal to 0, so that means determinant of this equal to 0, only then this will, the solution of this equation will exist. So, we started from here and then we found out the values of, so this will be an n cross n determinant. So, it will have n roots in general. So, we would, by solving this, we would find p 1 square, p 2 square up to p n square, right. Now, what we do next is we have to, and so the argument was each of these eigenvalues will correspond to one set of eigenvectors, right. So, we know it's typically it is something like an eigenvalue problem. This equation after substitution looked something like an eigenvalue problem, and for each eigenvalue problem we have seen previously, we have already done that during our during most probably your mathematical methods courses, you have done it already, I am assuming. So, what happens is for each eigenvalue there is one distinct eigenvector, and each eigenvector for an n system of n particle, each eigenvector will have it is a column matrix. A column matrix will have n number of elements, right. Now, for total n number of such eigenvalues, we have n number of such distinct eigenvectors, which will mean there will be altogether n cross n, that means n square number of elements. Okay. So, that is what we have to, that entire set is something we have to calculate. Now, in order to do that, we have introduced a second parameter, and we have written the most general solution for this one as sum over L A k L e to the power I p L t. Okay. And I guess you understand why it is, why we need two indices and why it is justified, right. Now, we will develop from here and try to see what can we make some comment on the properties of this A's and P's. Okay. Okay. So, what do we do first? We substitute this into the original equation, and so if we do that, we can write this as minus p l square. So, basically this equation we can, after this substitution, we can rewrite as A k L, sorry, there will be an A factor, of course, it will be A I j A k L, sorry, not K, it will be J L, right, the indices has to match, plus Bij A JL equal to 0. So, of course, there will be an exponential term which will cancel out from both these terms, right. So, that is why, because the summation is over J right now, the summation, if the summation is over L also, then we will have a problem, right. Yeah. Okay. No, sorry, it's not about summation, it is just that the term will cancel out nicely. Okay. So, what we do now, we multiply this equation, let us call this equation 1. Now, let us multiply this equation by A I L star from multiply this, and if we do that, we can write this as PL square A I J A I L star A J L plus B I J A I L star A J L equal to 0. Now, if I look at the matrix equivalent of these equations, okay, this and this equation, what is the matrix equivalent? Look at it carefully. So, the matrix equation to begin with was B A is equal to P L or rather, yeah, it will be P L square, no problem, A, right. So, what we did here, this operation essentially means, so this is the same equation, exact same equation in matrix notation, okay. So, these two are equivalent, just that when I open this, so matrix operation and write it by component, you will get this. Now, what I did here, I just multiplied this from this side with a dagger. So, once we do that, we have an a dagger on this side, a dagger on that side. Now, dagger means it is a transpose conjugate. We have to take the transpose of this matrix and conjugate numbers. So, if it is a row matrix or a column matrix, it will be converted into a row matrix and vice versa. Okay. So, this is to begin with, it was a row matrix, column matrix. So, this transpose matrix is a row matrix and each element of this matrix has been converted into its complex conjugate. So, that is why there is this A star. A star means complex conjugate. I mean, I am pretty sure you are familiar with these terms. If not, I think you can always check your mathematical physics textbook for this operations. Now, once we do that, now please understand this, without this matrix multiplication from left, this equation is a matrix equation. So, B A is a matrix, P square A times A is a matrix. Now, we cannot divide two matrices, that is not a defined operation, but once we do this multiplication, it becomes a number on this side, it becomes a number on that side, but we can, so we can always divide one number by the other. So, what we can do is from here we can write P L square is equal to A transpose B A divided by A transpose A, and this is a totally valid operation. But if we, instead of writing this, if I just write B A divided by A, this is not a valid matrix operation. So, similarly, the same equation if I write in component form, it will be P L square, which will be equal to B I J A I L star A J L divided by A I J A I L star A J L. Okay. So, this is one operation, this is one equation. Now, each of this column matrix, right now we do not know the nature of it, but all we know that if we do a general eigenvalue operation on a square matrix, we find out eigenvectors and eigenvalues, both are complex in general. Okay. So, if we are not sure about the nature of any number, a particular number, or which comes out as a solution of some equation, it is safe to take this as a complex number. So, if we do that, let us say a I L is a complex number in general. So, we can decompose into alpha I L plus I beta I L, right. So, where alpha and beta both are real numbers. So, combination of two real numbers and I is equal to root over of minus 1. Okay. So, these are two real numbers in with an I, it is okay. So, what I will first going to do is, it might be a bit confusing. So, I will just change this index, because these two i's might create confusion. Anyway, these are dummy indices. So, what we can do is, we can write j k, we can make it j, we can make it k. Similarly, this we can write j k, j k. Okay. So, this is totally valid, because these indices are anyway dummy indices, we are free to change it. So, it will be j and j. So, j star will be alpha j l minus I beta j l. Okay. So, now if I open the similarly we can write alpha k, sorry, a k l. Okay. So, if I substitute this 2 into this equation, what we will get is, I will just write it here. Okay. So, this once again, this is the complex conjugate operation. So, because these are real numbers, what we have to replace I by minus I. If they are complex number in general, we have to also include complex numbers of the complex conjugate of this one. But right now, because we have decomposed it into this format where these two are real, we just have to replace I by minus I. Okay. That is the complex conjugate operation. I am sure you are familiar with this. So, PL square is equal to, okay, open up this bracket and we will see. Okay, I am just leaving it to you for thorough calculation. It will be alpha j l alpha k l plus beta j l beta k l, and so there will be a plus I b j k, it will be alpha, okay, it does not really matter, because anyway this term will cancel out, we will see soon. It will be j, anyway let me try to get it right, I j l beta k l minus alpha k l beta j l, right, and divided by, it will be a j k, same term. So, it is identical numbers, identical terms in numerator and denominator. Now, if you look at this term, please understand that j and k indices are dummy indices. So, we are free to change it. What we can do is, if we interchange the indices, we will see that these two terms are exactly identical to each other. So, this term will give you 0. I mean, it is not that straightforward, because what we have to do is, we have to break it into 2. So, it will be, okay, forget about I, it will be b j k alpha j l beta k l will be b k j. So, we are just interchanging the indices, it will be alpha j alpha k l beta j l, but now please remember that B is a real symmetric matrix. So, if it is a symmetric matrix, it does not matter if we write k, so k j is equal to j l j k. Okay. So, now if I substitute it with jk, it will be exactly equivalent to the second term. So, not only this part, but if I do this operation totally. So, if I take this bjk inside and do this operation, basically open up the bracket, this term will give you 0. So, both sides will be identical. So, this will leave us with the following. Okay. So, similarly for aik, because only property we are using for that operation was real symmetric nature of bjk. AJKs are also real symmetric matrices. So, the same thing will happen to that. So, at the end these two terms, imaginary terms, will cancel out and we will be left with this. Okay. Okay. So, now let us look at this carefully. First of all the quantities are real. So, the matrix element for B's and A's, they are real, we have already seen. Alpha and beta, they are by choice, they are real, because we have chosen it to be real, right. So, this is how a total complex number can be expressed, as a combination of two real quantities including an I. So, the both numerator and denominator has real numbers, that means this quantity is bound to be real. So, one thing we immediately infer from this is the eigenvalues we have obtained is real. Also, if you look at it, kinetic energy T is equal to Aij Qi dot Qj dot, right. But once again we are now again dealing with quantities. I mean Qi's are combinations of A's, certain number of Ai's, right, amplitudes. Now, these amplitudes are in general complex. So, if that is the case, so we have to write this, if I want to write this in matrix form, I have to put a star sign here, which will be equivalent to the matrix operation Q dagger Aij Qj, right. Or rather I and j is not also required, because these are indices anyway. So, this will be the matrix operation corresponding to the kinetic energy. Now, please understand that this star is necessary, because now initially when we started we have taken q's at the generalized coordinate without any knowledge whether it is a real quantity or an imaginary quantity. But now we know at this point of where we stand, q's are in general imaginary. So, that is why this operation is needed in order to write it in this particular form. Otherwise, a simple transpose will do, right. If we find out later on that A's and Q's, these are all real quantity, we still need to do this operation, but I mean we do not need a star here, but you have to put a transpose here. Right now we are putting a dagger, that means transpose conjugate. If you just to recall, I guess, if some matrix A, dagger is A transpose of the conjugate matrix or A transpose conjugate. Okay. So, this is the dagger operation. I am pretty sure you are familiar with it. It is used a lot in quantum mechanics. Is one of the most well known Hermitian operations. Anyway, now if you do that and we write the Q as, or rather Qk as Al e to the power I p l t sum over L, right. So, if I take this particular form, it will be Al star, just a minute, it will be two indices. First of all, it will be Kl. So, if I substitute this for Qi and Qj, we will get some PL square A K L star A sorry I L star A JL, and that is it. So, T will be equal to this. Oh, of course. So, there is a Aij, totally forgot. And so, that means summation is implemented over I and J and L, all three indices, right. So, that will be the most general form of the or general form of kinetic energy in the current representation. Now, if you compare this part, you see this is exactly what we did, right. This operation, something similar operation we did to get the numerator, and similarly we can write potential energy which will be something like A I L B I J A J L, right. Okay. Yeah. So, once again the summation is over A, L and B. So, these are the terms we had when we wrote the original equation for PL square in the denominator and the numerator. Now, we opened up the bracket just to show you that this quantity is real. Okay. So, this means, but originally this was written as PL square is equal to B, what was it? Yeah, B J K A J L star A K L divided by A J L J K A J L star A K L. So, by virtue of these two relations we have got, this is something like potential energy of the system divided by kinetic energy of the system, right. Now, potential energy kinetic energy of a system which is oscillating, which is in motion, cannot be 0. It has to be some positive number. If in the trivial case when kinetic energy is 0, that means there is no oscillation in the system. Okay. So, this is a special case of so except for the special case when there is no oscillation in the system, the kinetic energy is always greater than 0. And similarly, potential energy, right now please remember that for small oscillating systems we are working in the we are working in the potential minima, and any deviation from the minima, if the system is even slightly deviated, it is a positive number. The potential energy which it is gaining is a positive number, and in case where the system stays exactly in the middle, it is a 0 potential energy case. So, the denominator of this expression cannot go to negative, I mean it has to be positive greater than 0, and the potential energy that upper and the numerator is greater than equal to 0. So, the limits of this is greater than equal to 0 and this has to be greater than 0. So, these two combined with this real nature, we also see that it is the quantity PL square is greater than equal to 0 for all the values of A's of the system. So, okay. So, we have two properties, one is this is real and then this is greater than equal to 0. Combining these two, we can safely state the systems, the amplitude the eigen frequencies we get by solving this equation, they are all positive definite quantity or could be 0, right. Now, once again what we do is we go back to this equation. Okay, so, keep this in mind. Now, we go back to this equation PL square A I J K L plus B J K A K L equal to 0. That was the equation we got after substitution for Q double dot and Q, right. Now, in this equation, so this is a series of equation and we will have for different values of L, we will have different different equations like this, right. So, in this equation, these quantities are already real that we have seen, we have, I mean, that is by construction of the matrices, these quantities are real. These quantities are positive definite or 0. I mean, either, I mean, it is not only real, but greater than equal to 0, that we have seen. Now, A k else will be a solution of this set of equations, right. So, if there are n such eigenvalues, we will have n such equations, and A k else will come out as a solution simultaneous of the simultaneous equation. Now, if all the quantities of this participating equation is real, we can safely state that A k else are also real. But this might be little too much, because sometimes what happens when we are solving for eigenvalue equations, we do not find out the absolute value of the amplitude matrices, but sometime we get them in the form of ratios for a given eigenvalue. So, what we do is we put one particular eigenvalue back, right. Oh, sorry, we get the differential equation for one particular eigenvalue, and we have to solve for the ratios. Okay. So, we can at least state, if this is not totally true, but we can at least say that these are real. Now, this could be real, and only if the phase factor between two between two amplitudes is of the form e to the power I phi, where phi is equal to either 0 or pi. So, we know that e to the power I phi is equal to cos phi plus I sin phi. Now, if you put phi equal to 0, then we get this term vanish, and we have cos phi is equal to 1. So, idea is there is no imaginary part in this. Okay. So, it can have no imaginary part only if the phase factor between two amplitudes can have either values of 0 or pi. If you put pi, this one again goes equal to 0, and this becomes -1. So, without writing this, we can also write that these are plus minus 1. Okay. So, the phase, I mean, okay. So, I would, okay. So, that was little mistake in my part. I should write them as, let us say, this is the amplitude ratio, the absolute amplitude ratio, that is the magnitude of amplitude, there will be a plus or minus sign here. Okay. So, this plus or minus is coming as an outcome of e to the power I phi. Okay. Fine. Also, let us do one thing, little more, and we will be almost through with this part. Let us do one thing. This is for one eigenvalue. Okay. Right. Let us write the same equation for another eigenvalue. Okay. Now, let us do one thing. So, it is just the same equation we wrote for another eigenvalue P m. Let us do one thing. Okay. Let us multiply this one with what, A j, yeah, let us multiply this one with A j m, right. Let us do that. If I do that, just give me a second. Yeah. So, if we do that, immediately by putting this number, we are summing over j as well. Initially, we were summing over, when this was not there, the summation was only on k. Okay. So, when we put this, the summation is over also j. Okay. And so, we have j m equal to 0, and so this one we just multiplied by A j m, and this one, let us call it 2, we multiplied by A k l, A j l. So, similarly, if I put A J L here and A J L here. Now, what do we get? Look at this operation here. This operation, now that we have proved that at least the ratios of this are, real. So, we do not need to take complex conjugate. We can only take transpose, and in element form, this equation can be written as A transpose B A. Okay. Because again, once again, please remember that J and K's are dummy indices. We can do the same substitution without writing in elemental form. We can also write this as B Kj, this one. Okay, just interchange these two indices. Kj will be A Jm A Kl, right? And please, and as Kj is equivalent to Bjk, we can write this as Bjk Ajm Akl, which is exactly equal to what we have up here. So, both these terms will actually point out to this matrix operation. I am just writing it in component, which is A transpose B A. Now, we have proved that A's are most likely real. We do not need a dagger, but we are good with the simple transpose operation. That's the difference. So, now if I subtract one from the other of these two equations, what happens is the second term, if I just make it plus, make it minus, this second term cancels out, leaving behind Pm square minus Pl square A Jk A Km A Jl is equal to 0. Now, in matrix notation, this is nothing but, okay, oh no, let us stick to the standard notation. Okay. So, these two terms are once again identical. So, A Jk A Km A Jl, sorry, let us stick to this. Now, if L is equal to M, what do we see? We see that Pm is equal to Pl and this term is immediately going to 0. If this is the case, then this is equal to 0 and A Jk A Km A Jl, which we can we can set, this is undefined. Now, if L is not equal to M, then this term is not 0 and we see A Jk A Km A Jl will be equal to 0. In order to maintain this equation, if this term is not 0, this has to be 0. If this term is equal to 0, this is undefined. Now, these two relations together we can write as, okay, first we have to because this is undefined, there is no fixed value to it. So, we are free to choose whichever value we are willing to put in here. So, if I set this equal to 1, then these two relations together can be combined to write this is equal to delta L M. When L is equal to M, this is equal to 1. When L is not equal to M, this is equal to 0, right. And this again in a matrix form is just this operation A transpose A, where small a is the kinetic energy matrix, big A's are the amplitude matrices, amplitude column matrices is delta L M. Okay. So, this is one relation, or you can put L here, M here in more general case. So, what we typically do is we actually have, let us say, 3 individual column matrices. I think we have discussed it already during the rigid body dynamics. If we have 3 individual column matrices A1, A2 and A3, we club them together to form one matrix which we call A. The first column will be A1, second column will be A2 and third column will be A3. Now, if we follow the same construction here, so this index will not be necessary because all capital A's and small a's are square matrices then. So, we can write this as this 1 under bar is the notation for identity matrix. Okay. Now, if we do that, simultaneously there is also another very interesting thing coming out of it. Now, look at the first equation again, okay, and in its pure form. In this particular form. Now, if this is the case, right. Right. So, in this first equation we have seen that this part, okay. So, this first of all this equation can be rearranged to give B j k A k l A j m is equal to P L square A j k A k l A j m. Now, this part we have already seen, this is nothing but delta L m. Okay. So, we can write this term equal to P square delta L m, right. So, once again this is also a matrix operation. In a similar manner, if I construct it in the A matrix form, we can either write it as A transpose L B A equal to P L square or delta L m, or in more general form we can write this as if we construct this square matrix out of A's, we can write this as A B A transpose B A equal to how do we write it? We can write this as P L. I think this is the best representation because this actually gives you a matrix. Okay, for this I am not sure what should I write. What I mean is this operation, this square operation with square matrix will give you a matrix in which we have P1, P2, Pn. So, it will be a matrix with where the eigenvalues are in the diagonal. So, that is what I meant, but let us write it as PL squared delta Lm. This is also a good representation. Okay. So, we have seen that at the end, if we choose this particular normalization condition, please remember this normalization condition that this is equal to 1 is a chosen value, and we always have to do it because normalization condition there is no universal norm on how to normalize certain quantity. So, we are free to choose, and once we choose that, we are simultaneously diagonalizing both kinetic energy and potential energy matrices in one go. So, that is the beauty of small oscillation. Here the mathematics is bit complicated, but we will take up examples in the next lecture and I will show you that in reality it is not that difficult, but once we solve the problem once for all, we are simultaneously diagonalizing both kinetic energy and potential energy matrices. Okay, so we will stop here for this class. In the next lecture we will pick up some examples and start working on them. Thank you.